A very good afternoon to all the team gathering here for the sixth day of teacher enrichment workshop entitled as Differential Equation and Mathematical Model. And we are really hoping that you are getting expert knowledge about the differential equation with respect to the different aspects. And as Professor Mittal sir is today's speaker for this session, and sir has very wonderfully elaborate each and every concept in detailed manner in the previous lectures also. And we are hoping that all the participants are really gaining in-depth understanding about the considered topics. With these words, I would like to request Professor R.C. Mittal sir to please start the session.
Okay, thank you, Dr. Lakveer Kaur. I just present the entire screen, then let me talk about. Is my screen visible, please?
Yes, sir. Perfectly fine, sir.
Okay. So, friends, as I told you yesterday, uh, today agenda is about massless methods and using RBF or radial basis function in massless method. So, to begin with, what is a massless method? Uh, just see that we have different kind of method which are available today to solve a differential equation or for that matter an integral equation. Uh, when I talk about differential equation, then you are given a domain in which the differential equation is valid. So you are given a domain in which uh, a domain in which your differential equation is defined or valid. But when you come to the what do you call your numerical solution or computational solution, then this domain, which is in general could be of different kind, which could be multi-connected or can have different kind of shape. So you have different kind of methods, but whatever method you choose, somehow you have to have a finite number of points in the uh, domain so that you can form your system of algebraic equation or different ordinary differential equation, and you then try to solve it. Now, if I talk about finite difference, which I took yesterday and day before it also, in finite difference, when your domain is regular of some kind, and then we first select uh, step length h, and then we draw a mesh with the help of h, which could be uniform or non-uniform. Meaning thereby is that we have certain finite number of points, and then we try to approximate solution at these finite points with the help of finite differences. And then applying the finite differences, we do for all the points, so that equation for different points are written and they are put at the one place, which could be written in a algebraic equation form. As I said to you earlier, these algebraic equation will be linear if the given problem is linear, and will be non-linear if the given problem is non-linear. But one of the serious drawback with the finite difference method is that it is good when your uh, domain is well behaved domain, a regular domain, some kind of rectangle, or I am using polar coordinate, then some kind of regular uh, uh, circle or cylinder. But if your domain is not uh, this kind of regular domain, then finite difference create its own problem because it cannot solve problem in every shape. It can solve only some regular shape. But nevertheless, story started with them. Then you have a finite element method, and you also have uh, boundary element method, and you have what you call your the finite volume method. Then some spectral method, other methods are also available. I will talk about in the context of massless method about finite element, boundary element. Uh, Subsequently, let me first tell you what a massless method is. So as I said to you, whether you use boundary element method or you use finite element method or you use finite difference method, you have to draw certain kind of mesh. You have to select uh, some kind of mesh where you are going to solve. But when you talk about a meshless method, then this mesh is not to be created. This mesh is not to be created. What you need is certain finite number of points which you can select based on some theory, and you try to solve the problem on these points so that error in the solution is minimum. Is minimum. So, friends, that's what your what do you call uh, finite sorry meshless method is. So I just come to first to make my point clear, let me tell you something which is very essential to every student should uh, understand that about finite element. Then I will go to further things. So my finite element method, friends, I am given I'm not taking initially problem, but that also can be done. So I am given a differential equation which I write Lu equal to F in omega with U equal to G. So I'm writing X bar. It could be uh, single dimension or two dimension or larger dimension in gamma, which is boundary of omega. Now, what we do in the finite element is that this my omega of this shape is divided into number of small elements, which could be a line in one dimension. In two dimension, it could be a triangle or rectangular or what you call your hexagon. Only these are the things which is possible. So I divide some way in the what you call your uh, element, small element, like this way, like this way. And so on, and so on. So first is that the mass is to be divided into what do you call your uh, triangle or rectangle or hexagon. Then you take one element, typical one element. Let's say you have triangle. Then you find the solution first in one element, typically. And to do this, what you do is that uh, when you say you are using finite element, please try to understand me. There are two ways to solve a differential equation numerically. One is that uh, by uh, differential equation is exact, but my boundary is approximated. Then it become boundary element, that I take a formulation where differential equation is exactly satisfied, but I take approximation on the boundary only, then it becomes boundary element. On the other hand, when I say finite element, my problem is like this. I approximate the solution on the in the domain, and boundary is exactly satisfied. So my boundary is not approximated. In massless method, you approximate both boundary as well as in the interior of the domain. So what I say is that typically what you do is that you take an element, try to find the solution in this element. For this, you take what you call weak formulation. You weak formulation. Why you take weak formulation? Because finding solution in strong form is rather difficult. Now, those of my friends who do not know what is a weak formulation, a weak formulation means we assume a solution uh, which may not the assumed solution may not have that kind of continuity and differentiality as the differential equation desire. What I mean to say is, uh, if my equation is y prime double prime equal to fx, then I assume a solution y, it should be uh, double differentiable. Y double prime must be existing for this problem. If it does not exist, then how can I satisfy the differential equation? But what we do is that I can take a formulation where y is uh, having only first derivative. So I convert the equation into integral formulation, which is a big formulation. Theory is available for that. And this big formulation desire that y must be continuous and y must have only first derivative, and you don't need second derivative. You don't need second derivative. So we are relaxing some condition over the solution. That's called a big formulation.
Yes, sir. VV Sharma also explained something about weak solutions in Berger's equation, like.
Okay. So fine. So what I mean to say is, I come back to this. So what you have is that you have differential equation. I divide domain into a small, what you call, element, which typically could be in 2D triangle or rectangle or hexagon, nothing else.
Sir, my question is that it's like a one single kind of arrangements in this, or it can be a mix of triangular, rectangular, or hexagon.
It is all your choice. Generally,
Okay.
people take only one element, but people have also taken mixed kind of without
Okay.
any problem. Theory says that you should know how to find solution in one triangle, how to
Okay.
find solution in one rectangle, and
Okay.
how to find a solution in one hexagonal. Hexagonal is a difficult thing, but
Okay.
people take normally triangle or rectangular domain element. So uh, taking typically big formulation, you find solution in one element. So you first form form the solution in uh, form approximate solution in an element typically. Now, whatever you are doing in L element, same kind of thing you need to do in each element, other element. Once you have in an element, same kind of thing you do second element, third element, they are numbered. Uh, and ultimately, so you know how to do, how to find solution in one element. And accordingly, you know the solution in other element of the same kind. Now, those who know, once I choose my element, it is a rectangular or triangular, the shape function or uh, s- shape function for that, uh, or basis function, people say basis function also, will be chosen according to your element, and then you put in the you find the solution in each element. Ultimately you assemble them, satisfy your boundary condition which goes to right hand side, and ultimately solve it. So you get the some kind of solution at each node of the element. So I have triangle, it will be having 3 nodes or more nodes I can take if I read more accuracy in the triangle. So I take middle point of the sides of the triangle depending on which kind of quadratic or linear shape function you are choosing. Similarly, you will be having rectangle, so you will find solution for bilinear element in terms of these 4 nodes. And once you know the solution in one node, 4 nodes, you can find solution in the interior of the element. That's what uh, basically your finite element is. So finite element is coming from the basically from civil engineers. And you know what civil engineers they have to
Sorry,
do.
sir, disturbing you. Can you explain this concept that you have just started from this line? We just construct the solution in our element, any of the element, right?
one
Approximate solution,
Typically one element.
any triangle, whatever we can choose. Uh,
No. There are 3 kind of element which
yes,
can
yes.
be chosen.
Okay,
Yeah.
right,
And
right. Suppose, but if I fix the arrangement, say let all, I'm just discretize my this domain into say n triangles,
mhm.
and then we are going to find an approximative solution on each and every triangle, right?
First I say my elements are triangular.
Okay, right.
Then my shape function for the triangle will be defined.
Yes, this is what I'm asking. What about what I mean? I really this concept is new for me. Shape function.
Shape function B is basis function or shape function, because ultimately what we do in the uh, finite element age is that, let me please, I
Yeah, because this is important. Otherwise, I will
no problem, no
understand
problem,
radial basis
no,
function.
no problem, no problem,
Yes, sir.
please.
Yes, sir. Sorry,
Uh,
sir, but I want
no
to.
problem, no problem. I just tell you, I am here, then I take new slide, please. So let
Yes.
me take a new slide and then go here. Okay. 100%. Okay. So what I say is that once I have taken my triangular element,
Okay.
just a minute, please. My things are okay. Ore baba re. I'm taken wrong pen. So what you have is, once I've taken my triangular element, then I
Yes.
have to choose shape function, which could be linear or quadratic or cubic, as the case be. Right? Now, what we say is that I write my solution as alpha I alpha ij eta xy, where eta ixy is the same function. Now, this same function is such that each node it is one. So my eta xy will be having property as the vertices xi, I say xj, yj, it will be one.
Okay. Okay.
Okay. And
Okay.
then, and in the interior, any
Okay.
point, any point I take in the interior, suppose
Okay.
this.
Yeah. Okay. 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 I
So,
understand now the
so,
point.
so the
Yeah.
solution will be in terms of this triangle for
Sure. 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 Yeah.
point, and then this and this. So you have theory how to define your save function, and you know how to get triangular save function or quadratic. When I take quadratic, I need more points, so I take middle of this, and then quadratic save function can be chosen. So you need two things: save function as well as the what do you call your element, and save function depends on the element.
Okay. Okay. The basically shape functions matlab we can find out any other value.
We are interpolating the solution in the domain.
Yes, yes, yes.
That's
Now
the.
this is the line. Yeah.
So because if so, what is typically is that I write my solution in the form of Lij at eta xi y, or the element wise. Okay. So what happen is that one of the beauty with the finite element is that you can find the solution only with the help of element only, because you don't have to consider the whole thing. What is happening is that my domain is there, and I have divided into number of triangle or rectangle. Then suppose I want to find solution here, then all other element will not be important. Only this element which is coming in which the point is only its
Line.
its
Okay.
vertices are important. The solution at that vertices, those vertices you have with you, and you can get the solution very well.
Okay. But it's you are talking about like finding this function at given particular point. But if we want to know the whole function, I mean,
That's no, please understand me. I think you are not getting my point. I choose my uh, element. My element is triangle for the sake of example.
right?
Then my second job is to construct my save function.
Okay.
So my construction of save function depends on what kind of save function I want, whether it is a linear or quadratic
Okay.
or cubic and so on.
Okay.
Okay. So if I decide for the sake of simplicity, I decide that my save function will be linear. Then for a triangle element, for linear save function, only three vertices are sufficient,
Okay.
right? Now, the one of the property of each save function is that they are unity at the node of the element. So my suppose I call three points as A, B, C, then eta I x y at A is 1, eta I will be having then three save function, but anyway, eta I at B will be 1, and eta I at C will be 1.
Okay.
Right. Now what happen is that if I take any point interior to triangle,
Okay.
then very centric coordinate system is there. So the area of this triangle divided by the area of the whole triangle is the approximation at the point P, which is inside, right? And then area of this triangle divided by uh, the area of the whole triangle uh, for the B coordinate, and so on and so on. So you have very centric coordinate system, and then you get all three values for a triangle, which give you the whole solution. The beauty with this is that if P goes to A, it becomes automatically 1, because both the area coincide. So otherwise there will be three triangle, and their ratio of the triangle area of the triangle divided by the total area of triangle will give you the value at that point. That's what it is.
Okay, sir. Okay. Thank
So,
you, sir.
so you have the save function, you have the element, but my concern here is that when you use finite element, you use the elements which is mass created for the domain. Now, if I use boundary element, if I use boundary element, then what element is there? Because this point uh, everybody can understand very easily, because we teach Green's theorem, Stokes theorem in. So what uh, Green's theorem does is that it connect area to the boundary, to the boundary. I hope everybody understand that.
Yes, sir. Yes, sir. Yes, sir.
Right.
Yes,
So
sir.
Green's theorem is a double integral can be converted into line integral, or line integral can be converted into double integral. That's what basically theory of Green's theorem is. What I say is that I can formulate the problem which is given inside the area, but in the form of boundary. That is, my differential equation will be exactly satisfied. Delta comes in the Green's theorem. I hope you remember that. And so the any Laplace equation or equation which has harmonic function can be converted into in terms of the boundary, and solution can be obtained with the help of the boundary only. You don't have to discretize interior of the domain, but you can discretize only your boundary only. And so meaning thereby is that you will be having uh, elements which are much lesser than a finite element, and you can get better solution. To put my point very precisely, I keep on talking about Poisson integral. Now, what Poisson integral does, this is a boundary element method for me. Poisson integral does is that a solution at the inside of a point in a circle is obtained with the help of the value given on the boundary of the circle. Because if I write my what you call solution u r theta in Poisson integral, it is nothing but uh, uh, this is 0 to 2 pi 1 upon 2 pi uh, g theta, which is given on the boundary, r square minus small r square upon r square minus 2rr cosine theta minus phi plus small r. This is what no, theta phi, please. This is theta is here. So phi. So this is what Poisson integral is. And what is zeta? G theta? G theta is on the boundary. So if you know the boundary value, the solution at any interior point can be known. I hope point is clear to everybody. So it is the solution inside the domain is depending on only the boundary values, nothing else. And so I have to bother about boundary only. I have to find the integral on the boundary only, nothing else. So this is some kind of boundary element, or the apply Green's theorem, where the differential equation will be satisfied, and you need to find only values at the boundary, so that solution inside can be obtained with the help of the boundary. That's what the boundary element is. Yeah, anybody, any type of question or query or suggestion, whatever it is. Okay, so
Sorry, just a second. I just want to ask you one thing, that as you said that boundary element method is basically like where our solutions are exact and boundary conditions are approximated, right?
yeah, true. No, please try to
Or
understand. Try. Yeah, I got your point, but
okay, okay.
let you put the things
हाँ
in
बस
proper
थोड़ा सा मैं उस पे हाँ इसको
proper form.
करना चाह रही
Okay,
थी.
proper form. Let me put you. I have my differential equation,
Yes, sir.
and I have to solve my differential equation. This is my differential equation. This is my boundary condition.
Yes, sir.
Right
Yes.
now, there are three things which are with me. First is that my boundary conditions are exactly satisfied. I again say my
Okay. Okay.
boundary conditions are exactly satisfied, but I am taking approximation for the differential equation which is valid in the domain. You know,
Okay.
the
Okay.
the domain of what you call your your differential equation is valid in the domain only, while u is valid on the boundary only. So in the second case, my differential equation is exactly satisfied. Meaning thereby is that if my equation is not exactly satisfied, I will not have boundary element formulation. My Poisson equation will not be valid if it is not exactly satisfied. So it is exactly satisfied, but it is converted in the form of only boundary. So I'm now approximating solution at the boundary, and when I
Okay.
approximate a solution on the boundary, my interior solution will also be get approximated. But
Yes.
my formulation is based on that. My the differential equation will be exact, and I am getting the approximation for the boundary only. I hope my
Yes, 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 yes. Now it's clear, sir. Yes.
भाई, परेशान मत करो यार. So this is about
Using this Green's theorem, now we can convert our boundary this element method. We are just taking a bridge of this to the surface, basically, right?
yeah, true. That's what I'm doing.
Yes, yes,
So just I want to explain, but a boundary element method is not always possible. If possible, then they are much accurate than your finite element, because finite element needs more points, boundary element needs less points.
yes, sir. Okay, sir. Okay.
So now I come to my radial basis function. So what the point which I would like to tell you again, massless method will be much better than boundary element as well as what you call your finite element, because they don't have to create any mesh. I hope you try to we have to select certain points only on the boundary as well as in the interior. Uh, I hope my point is taken in that way. Uh, then let me come to by what I call then let me come to what I call uh, let me select pen please.
Yes, sir. Yes, sir.
So yeah, so I come to first what is my radial basis function. What is my radial basis function? Radial basis function is a function from I write this way so that difference can be seen by you. RT to what you call uh, R. So from my T could be 1 or 2 or 3, or in other domain it could be higher dimension. So I T is some dimension. For differential equation it could be 1, 2, 3, but in machine learning or something it could be of higher dimension. So from a higher dimension I'm going to a real value, and this is nothing but phi of r. This is defined as phi t is equal to or r equal to something which is a function of so I say phi of x. X is a vector here which is nothing but x bar minus I take c here, this. So what I say is that this is nothing but you can say uh, a real valued function, single real valued function R, whose definition depending on whether you are in the one dimension or you are in two dimension or you are in the three dimension. In the case of this is as I said to you, give you distance from a fixed point C, and C is called what you call your um, parameter, which is a shape function, shape parameter, shape parameter. What I mean to say is you have a vector which is belonging to p dimension, and you get a value which is a real value which depends on the distance of a point from a fixed point, which I call here c, and this will be a real value, and its definition will be changing with the what you call your dimension. To make my point very precisely, those of you who know uh, C++ or C, this function phi r is uh, is a good example of what you call function overriding. Function overriding, I again say, not overloading, I'm saying overriding, which is nothing but when you define a function in the derived class, then it will have different values. So when r equal to 1, distance concept is only uh, x minus x naught, distance from x, which is always positive, so I say positive. If I go two dimension, my things will be x minus x naught whole square plus y minus y naught square. And if I go to three dimension, my distance will be x minus x naught square plus y minus y naught square plus z minus z naught square. So the definition of distance will be changing with the dimension. So if one dimension, two dimension is subclass of one dimension, and keep on doing so. I'm just giving example, but it's not of interest to everybody. But anyway, overriding is a good example of it. So what I say is that you will get different uh, if you vary the point, you will get different value, and the value depends only distance function r, so it is called sometimes uh, single valued function. Now if you want to understand more, then I have different type of RBF which are in use. The first is phi r equal to r simple distance we take. If I take cubic function, then phi r is r cube, and then r is function of x. Please try to understand me. So r is the distance, and monomial, then I can write phi r equal to r raised to power 2k minus 1. Then there is something called cubic method, which is given by the definition by uh, this. Then thin splines, where which is in the log form. Friends, I'm not interested in this. My main concern is uh, this function, which is e raised to power epsilon r whole square, please. This is my what you call Gaussian, which is normal distribution radial basis function. Then second is multi-quadratic, which is written in the form of 1 plus epsilon r whole square. Then inverse quadratic, so quadratic 1 by that, so this is inverse quadratic. And then you have inverse multi-quadratic function, which is this is quadratic, this is a multi-quadratic, so this is under root here. So you have different kind of what you call Gaussian function or multi-quadratic function RBF. So they are different kind. Some have more property, some have less property, but one uses commonly Gaussian function, multi-quadratic or inverse multi-quadratic. They are used very much in the theory. So why they are in use, please understand that also. So if you see some of the function, they have typically property that they are uh, concentrating to a single point, and as you go away, then things become wider or lesser depending on the parameter I use. So this is what you call your linear radial basis function, phi r equal to r. This is quintic, that is phi r equal to r5. So but the point is that much energy or much area is near the point where you want to approximate the thing. The same way, this is what you call your Gaussian function or normal distribution. And most of you are aware, when I take my mu and epsilon, sigma correctly, energy is much in this area This is when you have is worded thing. So the just parameter value is here 0.01 and parameter value here is 1. So you can understand that way. So very much depend on the parameter or say parameter uh, uh, C or epsilon, whatever it is. Then you have multi-quadratic function. So they are having this shape. Uh, Point is that uh, much information is near the point where you want to, you have taken your point around which you want to approximate. So this is the cubic pattern for what you call parameter 0.1, and this is for 1. This is a multi-quadratic, and let me come back to my thing. So what is the problem? I have RBF. I will use Gaussian mostly, or multi-quadratic, or I will use quadratic, uh, um, inverse multi-quadratic, IMQ. Gaussian means E minus CR square. Multi-quadratic means I have already given to you R square plus C square simply, and inverse multi-quadratic is 1 upon under root R square plus C square. That way. Now I am why they are popular. Now I am given my y equal to fxi some data I equal to 1 to n. The problem before me is that I want to find an approximation or interpolation for my function y. So let's say my y I can write in terms of I want to n alpha I, the constant which are to be obtained uh, in terms of my phi x, which is nothing but in terms of r. So I write phi of mod of x minus what you call function x I will be writing. So I is there, so I keep on changing my center and I will be having this. Now when I do so, uh, uh, this is my approximation, and I take then I equal to 1, I equal to 2, I equal to 3, and I will be having y1 equal to I1 to n alpha, sorry, uh, I write, oh, no problem, I equal to 1 to n alpha I phi of what do you call your, uh, this is written here. Uh, this is okay, please. So I take my point as j equal to 1, 2, 3. So I will be having something like y equal to I1 to n. So this is yj alpha I phi xj minus xi. So I will be having in this form. And now if I write my matrix, please understand now. What I will have is that a system where you have matrix A and you have your alpha 1, alpha n, and you have your right hand side, which is y1, y2, yn. What is my A? See that aij is equal to aji because of the way I am defining my function. So my function is this. This is a mod sign. If I change j by I or I by j, this phi remains the same. So when phi remains the same, my matrix A will be a symmetric matrix. One thing. Second thing is that my typically I will be having this kind of, if diagonal will be all 0 because distance will be 0. So if I don't use C, then this will be 0. And then this is some distance D1. So I write this will be always D1, then you will be having D2, D2, and you have here Dn. Similarly, you have something like symmetric matrix D1, D1, and you have Dn here. I hope my point is well taken. If any issue, please let me explain, because I might be doing other way. Yeah.
Yes, sir. No, the whatever you explain is okay, but I just want to understand what you exactly want to show here. You just started generally here with a function with some given data.
Interpolation problem.
Interpretation. I mean, right now you are not using this RBF for solving the differential equation. You are
I,
just giving us some
no,
idea.
I'm putting you the basic thing. Nothing else.
Yeah, yeah, yeah. You are clearing the basics. Okay, okay, okay.
Okay. Please understand this problem. Then I
Yes,
come to
yes, yes, yes,
I'm coming to in differentiation too.
yes, yes.
Please,
Actually,
please
I just
don't bother.
uh,
I will take very fast then.
okay,
Okay,
fine,
okay,
fine.
no problem. So what I say is that you have this matrix A, which is uh, Aij is equal to symmetric matrix, and this matrix is called top-leaf matrix. What is the top-leaf matrix? A matrix called top-leaf if
Yes,
its diagonals are the same. So it
same.
is a typically top-leaf matrix. Now, what is the problem? Problem is that my A should be invertible. A should be invertible. That is the problem. That is, if my A is invertible, then alphas can be obtained. Then my radial basis function can be used for the interpolation. That's the point which I want to make. Right. Now, in general, what is happening is that it is a symmetric matrix. At the same time, it is positive definite. Positive definite. That is, inner product AX is always positive. I hope people understand what I'm saying, talking about. Uh, that is, if I write, I take any vector and multiply it by A, then I take inner product with X itself, then it comes out to be positive. And so it called strictly positive definite, right? Otherwise, it is greater than or equal to 0, then it is simply positive
Definite.
definite, or
Semi-positive.
semi-positive definite, and so on, and so on. Now, since the matrix is positive definite and symmetric, it is invertible. It is invertible theoretically. But practically what happens is that when my n is large, then it tries to be what you call condition, what you call ill condition matrix. For n large, it tried to be ill condition. That is, computationally, it is not possible to find inverse or to solve the system, because a slight perturbation in the coefficient makes a huge difference. That is ill condition. What is the condition number? If you understand that, then you will understand what I mean to say. So my condition number is norm of A into norm of A inverse. It's called condition number. So my condition number of A uh, is large. That is, my system is ill condition. Normally it should be near 1, but it becomes very large value. Then it becomes condition number very large. That means system is very sensitive to the perturbation, or the ratio of the maximum eigenvalue and the minimum eigenvalue of the matrix. The maximum and minimum, they are having a very high ratio, They are not very close enough. They are not very close enough. So what I mean to say is, since my matrix is invertible, theoretically interpolation is possible, but but it tries to be ill condition for large n value. So for large n value, it is ill condition. And so one has to do something. One is that since it is a positive definite matrix, For small LL transpose LU decomposition, its Cholesky method can be applied. For small or medium thing. And this also can be solved because it is a symmetric as well as positive definite. So conjugate gradient method can also, iterative method can be applied. Method can be applied. On the other hand, for large n, one can use a precondition, a preconditioner. That is a matrix which makes it well conditioned. If you have anything more discussion on preconditioner, I can discuss about the, I will go further. So the issue using uh, radial basis function is that uh, for three radial function, in general, the matrix is positive definite, the Gaussian, the multi-quadratic, and inverse multi-quadratic. The solution is possible, but for large solution, large n, it is ill conditioned, and so one has to apply some kind of precondition and solution can be obtained. Now, this much about interpolation problem which is occurring while you solve the problem, because as increase n, it becomes unstable and things are not good. But for a small n, it is done. Now, before I go to my what you call, I have 7 minutes. Then machine learning. First, let me come to application of uh, learning application of RBF. Then I come to the differential equation. So having defined RBF, radial basis function, then let me, I have, it is interpolation is possible. Now, simply putting what we do in the machine learning. In the machine learning, we teach the machine to uh, uh, to behave in a particular fashion as a, or we introduce artificial intelligence in the machine so that it can recognize certain pattern which are there in the data. So there are two parts that you train the data and then you verify it. So train and testing. That is what you do basically, that data. Now, what is happening is that your data is linear, then things are okay, and you can have regression, uh, uh, which is typically linear regression, and you can teach the, with the help of data which is large, that you have some kind of alpha xi plus bi thing, and so the yi here because I have bi here, so you have this I can write j so that there is no confusion, right? So what you have is this linear kind of regression, and you can uh, interpolate the data. First, you find your alpha j with the help of training, and then you test the data, and your bi and the alpha j's are obtained, and then you give a new value, some new value. Then that new value will be uh, recognized, and it will say this value is this. Basically, what you have to do in the uh, machine learning is that you have to identify the classification of the features. So what you do is that you divide the data into different classes, and then a new data is given to you. Then you want to see which class it falls in, and accordingly you decide that this is this kind of feature or this kind of pattern. That's what you do in the, basically in the, what you call your uh, linear program, sorry, machine learning. Now, if you have your data as your non-linearity, it's very difficult to decide classes. So in order to have classification of the data, which is a non-linear type of data of non-linear type, it's not very easy to find classes otherwise type. Then what you use is you use RBF as as interpolation. Polation, and you are able to linearize the data with the help of RBF, to put very briefly. So what you have is that you have a data which is very difficult to find different classes because it is scattered, distributed, and then you have to transform the data in a such a way that you can linearize, or you can say certain kind of interpolation can be made so that your classifications are made. This is done in two ways in the machine learning. One is the artificial neural network, ANN, with so I write artificial neural network, or you have what you call SVM, support vector machine, ANN, and support vector machine. What is the kernel? In the a kernel, what it does is that there is a kernel. You take nonlinear data, put through the kernel, it becomes linear data. So what you do basically is you choose RBF as a kernel in the support vector machine, and when you use RBF as a kernel in the support vector machine, your nonlinear data which has scattered classes, points in the classes. So in order to make them well behaved, you pass through the support vector machine kernel through RBF, so that data is uh, uh, very clearly distributed in different classes. That is done with the help of RBF, depending on the dimension of the data, or depending on the features of the data, number of features of the data. So each feature is a class, and you do the classification. On the other hand, the artificial neural network, what you do is that you do that you have in the artificial machine is nothing but your something like brain, which is called neuron. So you have what you call input layer, and you have hidden layer, and you have output layer. What is the meaning? To your brain, you give certain data, informations. There are neurons in your brain, you give that information, neuron analyze it and give you certain kind of output. And by this, you gain an experience. And then a new thing comes to you, you decide that this thing is this. So that's way you have input, and then you have hidden layer. In case of artificial neural RBF, I say basically RBF, uh, artificial neural network, your hidden layer active functions are RBF. Hidden layer of active function are RBF. That's what you do uh, when you have a neural network. So in both cases, the purpose is that there are weight functions. Those weight functions are to be compared with the exact value, and there is a error. This error is to be minimized. So you have some optimization in both cases, and then you get weight function. Once your weight function or alpha is are obtained, your interpolation is there, and now you can have different classes of the data. And then new things comes, you try to match which class it falls in, and you decide this is this. That's what you do in the machine learning. And RBF are done when you have unsupervised learning, and there are the different method, but the most popular method are neural network, and you have support vector machine. And in a support vector machine, the kernel is RBF. In case of artificial neural network, there is a hidden layer, and active function in the hidden layer is again RBF. This is much information I just would like to give you. Then I come to my what you call your uh, uh, the differential equation, how to find uh, solution of differential equation with the help of RBF. So let's take simple example. So I take simple example. I have a function u double prime equal to fx. That is my boundary value problem, which is defined between 0x, let's say 1. And then I have at u0, you are given something alpha, and at u1, you are given something like beta. I hope you understand my problem. This is a 2-point boundary value problem, simple 2-point boundary value problems. Now, what I have to do, I have to approximate. So this is by uh, 0 to 1, and I take step length h. So I select my point. Uh, I select my point as equidistant. That's, I'm not drawing mesh, but I select my points at equidistant. That's what I do. So this is I'm doing. Now there are 2.0 and 1. This is to be so value of u at 0 and value of u at 1 has to be interpolated by RBF, and then that RBF is to be approximated in the interior for the double derivative, and I have to give the solution. So if I write my first equation, that is so this is my x dot point, this is my x1 point, this is my xn point. Then if I write my first solution at 0, that is at x is equal to 0, my solution will be summation j 1 to 0 to n plus 1, because this point is n plus 1, aj phi, then you have x minus xj, my basis function, which I will choose which kind of basis function I should choose. This is equal to what you call your f of what you call 0, f of 0, first point, x0, right? Then similarly, if I take the last point, which I will take, now I have to find in the interior. So in the interior point, my approximation will be given by uh, j equal to 0 to n plus 1 aj phi, uh, I'm sorry, please, this is my alpha, this is my alpha, this is my alpha given to me, phi double prime x minus xj equal to f of xi, where I is going from 1 to n. And then I have to write at x is equal to 1, which is equal to j equal to 0 to n plus 1 aj phi x minus xj is equal to beta. So friends, since boundary are yeah.
ये समेशन पे आपका 0 to n ही नहीं जाएगा, पॉइंट्स n+1 है, but summation runs over from 0 to n only, isn't it?
You are very correct. N plus 1 points है, पर ये 0 से n तक है. Yeah, you are very correct. I'm sorry.
अब मैं एक बार फिर से रिपीट ये समझना चाहती सर, जो दिस इज यू आर टेकिंग एन अप्रोक्सीमेशन एज पर द डेफिनेशन ऑफ द रेडियल बेसिस फंक्शन, राइट?
Yeah, so I will choose my radial basis function.
So this phi is basically arbitrary, that is what, na?
Which one?
This phi function is an arbitrary.
No, I will fix phi. I'm not taking arbitrary. For any basis function, this will be formulation.
This is formulation, this is definition, and this is formulation, but you will, in the end, you will define what your phi will be, right?
I will take a different kind of phi and tell you what is there.
Okay.
And in this case, my h will be 1 upon n plus 1. I hope that's clear. That's why I get a confusion. So that's okay. Hello.
Yes, sir. Yes, sir. Yes, sir.
So what I have is basically a, and I will be having something like
In the second
a0.
equation, you have I goes to n minus 1.
Which one?
There are
No,
total n plus 1 equations,
no,
right?
no, 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 no. That's I thought you were asking same question earlier.
No, no.
No, but just no,
ज-
because I have
यहाँ
total.
पर
हाँ जी,
यहाँ पर
सुनो
जो आपने लिखा है I equal to 1 to n. The
I'm
second.
understood. I got your point. Please
Yeah.
listen to me. Please listen to me.
Okay. Okay.
My total points are 0 to 1. Right? My total points are n plus 1. x0, x1, xn. Hello?
Yes, sir. Yes, sir. I'm listening. Yes.
So x0, x1, xn.
Right.
When I take approximation, I have to take approximation for all the nodes.
Okay.
So my x0 is a node, x1 is a node, x2 is a node, xn minus 1 is a node, xn is a node. When I take my approximation at x0, it is a boundary value. So I will give only equation for the boundary value with the help of basis function. So this is my alpha is a boundary, and I have taken j equal to 0, aj phi x minus xj, simple phi because it's a simple interpolation, no derivative involved, equal to alpha. And
Okay.
same thing here. It is going from 0 to n, so all note. So all note. So this is also going from 0 to n, aj phi x minus xj equal to 1. So x here, uh, uh, you understand the points, and this
Yes.
is,
Basically, it's a group of equations, but you just mentioned it for 3 different cases
yeah.
for the
So
boundary points.
yeah. So this is 0 here, and this is n here, and this is uh, I here.
Right.
Yeah, I here, right? And I
Right.
will be having this matrix a0 a1 is equal to first alpha, last beta, and I have my f1 to fn minus 1. Confusion slightly, no problem. Yeah, it's okay.
Yes, sir. Yes, sir.
Okay. Now I want to know what kind of matrix A would be. That's my job. Okay.
Yeah.
So
Yes. Yes.
so my job is what kind
सर
of yeah.
वन 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 जो ये डबल डैश आपने वाई फाई के ऊपर डाला, ये बाय मिस्टेक डल गया है क्या?
Huh?
सेकंड इक्वेशन में फाई के ऊपर डबल डैश डेरिवेटिव इज नॉट डेरिवेटिव ना?
No, it's derivative. Oh, Baba, please try to understand me. My domain is from 0 to 1. Hello.
यस सर. यस सर.
So
यस.
x naught is a point which is a boundary. Xn is a point which is a boundary.
राइट.
X1 is an interior point.
राइट.
So is x2. So is xn minus
एन
1.
माइनस वन.
Okay.
Yes.
When I come to x naught, it
Hmm.
is a boundary point. So my RBF approximation will be only for the simple interpolation,
Yes.
because quality of x naught is a boundary point.
Right. Right. Okay.
So this is simple interpolation, right?
Okay.
On the other hand, if I go to x1 or x2 for that matter, I1 to n, this is I here, please.
Okay.
Right? So then this becomes j here, or this I, this j, like that. So what you have is that when this goes this way, then since this is an interior point, my equation valid is only at the interior point is the differential equation.
Right. Right. Sir. Right. Right. It must satisfy the differential.
Because this is the interior point.
Right.
So my
right.
approximation is for interior, and this is for boundary.
Right. Right.
Right. So
Right.
so this is j here, this is j here, this is j here. Right. Now what happened is that, please try to understand me. First is that now A is not symmetric. Why? Because my first row will be for 0 and first column will be 0 as well as double derivative double. So this row and this column will not be same. Are you get my point or not?
Yes, sir. Yes, sir.
Right?
Yes.
And
Yes.
same way, this is the column for the last column and last row, they will be not the same. So this is not same as this is not same as this, so it is not symmetric. It's not symmetric. However, the other interior, if I leave first row and first column, last row and last column, then I have the matrix entirely defined by n by n minus 1 by n minus 1 matrix defined by the middle equation. It will be symmetric because they are all phi double prime. So this part is symmetric,
Right.
right? So
Right.
this is just show you that what is happening. Now,
Yes. Yes. Now I understand. Yes.
now suppose I take my phi h, what you call, so I take my phi x is the multi-quadratic function r square plus c square. This is my quadratic multi-quadratic phi x. Then my phi prime r, because I have to find derivative, so my phi prime r will be half r square plus c square minus half into 2r, which is 2 cancel with this 2. I hope I am correct.
Uh, okay. Yes, sir.
Okay. Then I come to what I call my phi double prime r, sorry, r. So this is equal to, I can write this as, this become r square plus c square. This is under root r square c square minus r half, uh, you have minus, so this become, uh, yeah, true, r square plus c square minus 3/2 into 2r. Is it okay or not? So this 2 cancel with this 2, and I have this as something like, no, this is uh, half here because I'm taking only this. So this is half here minus half here. That's right. So ultimately what I get is, if you see my thing, I will be getting this as c square minus uh, r square. No. So I get this as, let me complete it, no problem. So I have r square plus c square minus r square here, and I get r square plus c square raised to power 3/2, or this is c square upon r square plus c square. So I write 3/2, please. R square plus c square 3/2. Yeah, anybody any issue, please?
नो सर, ऊपर वाले में नेगेटिव आएगा शायद, माइनस आर अपॉन अंडर रूट आर स्क्वायर प्लस सी स्क्वायर. बाकी
हाँ, कहाँ
सेकंड
पे?
फाइव डैश आर इज इक्वल्स टू
हाँ
माइनस
हाँ
माइनस इज आल्सो देयर ना.
हाँ. So because this function is under root r square, so half r square minus half है ये, तभी तो मैंने नीचे ले लिया 3/2. Check it, no problem. This is correct.
ओके ठीक है.
Check it, check it. So what I do is that now my r is equal to xi minus xj, difference between xi minus xj. I hope everybody understand that. So this is equal to r is, so this is equal to, if I write to my thing, then I have to take the I minus j h, because xi is ih, interior, xi is ih, right? So xi is ih, so xj is jh, and I get this thing. And then my Tij become, if I write matrix Aij, I say Aij become something like you understand very well. C square upon what you call uh, R square H I minus J whole square plus C square, and this is H square. I hope you understand.
Yes.
Hello.
Yes, sir. Yes, sir.
So what I say is that you have this matrix where I find interior, and same way I can write my uh, uh, this line also, this line also, this line and this line are already obtained by me because this is coming from double derivative. So I can same way write this, which is nothing but simple function you have. So what is my phi? My phi is this. So I will write my phi h of phi r h under root r square plus c square. So this is nothing but under root I minus j whole square h square plus c square. What I mean to say is, the moment I write this, I can formulate now because phi value is obtained by me, and this xj minus I is nothing but r. So you have this matrix. This matrix is such that the interior part of the matrix is, if I leave first column and first row, last row and last column is symmetric, and there are many issues involved here. This is non-symmetric matrix, and hence for large value of n, for large value of n, it is ill condition. Ill condition. So you should take a small value of n, or what you do is that you take some preconditioner to make it well conditioned. This is the first thing. The second is that for a small value of c, small value of c, again it creates problem, ill condition. So C should be, please understand what is the C. C is a shape parameter, and when C is very small, C is coming in the diagonal element side. So diagonal effect becomes less. Please understand me. And when diagonal effect becomes less, diagonal dominance is lost, some kind of diagonal dominance is lost. So you have more problem. So C should be not very small. Your end should not be very large. If you do so, your solution will not be coming accurately. Now this is about if I take my function as multi-quadratic. So this is about multi-quadratic, where the values of this is defined for phi r, and this is defined for double derivative for phi double prime r, phi double prime, and aij can be obtained. Now, suppose I take my function h, what do you call inverse multi-quadratic. Inverse multi-quadratic. Multi-quadratic. Then I have the same kind of function which I can uh, uh, write. So when I write this way, then you have something like this. Uh, I just calculated, so I'm writing phi double prime xi minus xj for multi-quadratic, inverse multi-quadratic. That is, let me write function first. So 1 upon r square plus c square. This is my multi-quadratic function, and my phi prime xi minus xj. In this case, is equal to minus 1 upon h cube. Then I have g square minus 2I minus j whole square upon g square plus I minus j whole square 5 by 2. Of yeah, yeah, 5 by 2. So you have 5 by 2 here. So this power h, I write power, this power h 5 by 2 here. And my g is something like c by h. that is C equal to Hg, so that H cancel out and I have this thing. So what I mean to say is for this function you can find always multi-quadratic, you can find what is your value of uh, double derivative. And same way, if I my Gaussian function, if I take Gaussian function, that is phi r is equal to e raised to power what you call uh, minus r square upon c square. This form I am taking. In that case, phi prime r will be minus 2r e raised to power r square upon c square, and my phi double prime r will be what you call uh, I take this, then 2e minus r square upon c square, then I take minus 2r, so I take minus sign out, plus become minus, then it become 2r square e minus r square c square. And to put simply, my phi double prime xi x minus xj, xi minus xj will be equal to minus 2 upon h square uh, e minus uh, I minus j, because I put r square is equal to as you know, xi minus xj is equal to I minus j h. So I put that way, so it becomes uh, g square, g is same thing which I write there, into g square minus I minus j whole square upon g4, and g is your h by c, h by c. That's what let me check, g is uh, c by h, c by h. So what I mean to say is not very difficult to find what are your derivatives here. So once you get derivative, then you form the system, and once you form the system, you can solve it. You can solve it, but again say, for all these three, the problem is solvable, uh, but you should not take large value of n, and you should not take the smallest value of c, just some medium value. If you take large smallest value of c, then it also create problem, because your diagonal becomes smaller and things are then towards ill condition. um, I hope you try to understand my problem. Now same way, if I'm just telling you, if you have something like this equation, du by dy 2 equal to fxy, and with in a domain omega, with uxy on the gxy on the boundary, then again my shape function will be of the same type. I mean, say my phi function will be, I write in terms of r, which is nothing but under root, in the case of uh, your quadratic function, r plus c square. So I write same way, but now definition of r square is changing. My r square will be now under root uh, I h square plus j h square. This is my r square from 0. And if I take 2 points, I say point are x I yi and xj yj, then my r square will be, as you understand, under root I minus j whole square h square plus yi minus yj. I take h1 square here, h2 square here. So that will be the definition of my r square in the second dimension. Yes, please.
Yes, yes, sir. Yes, sir.
So the moment you get to the definition of R squared, derivative are already found in terms of R. So they can be found in the form of dr by dx and dr by dy. I have done some calculation, but really it's a lengthy one, so I don't want to say. But only thing is that this problem can be solved and your matrix can be formed and you get the solution. The point which I'm again and again saying is that inherently, this is a Kasha collocation method which I have discussed just now. Kasha collocation method. Kasha was the first person who gave in 1995-96 this method first time using quadratic or multi-quadratic your basis function RBF, right? And system can be solved. Now, if I come to uh, our contribution, let me tell you, let me talk about the kind of problem we have solved. Uh, then I, I just tell you that we do differential quadrature method 2, DQM, or what we call differential quadrature method.
Sir, there are like I just read that there are like co-location methods. So this is one particular kind of co-location methods that we just discussed here, right?
Let me tell you what collocation method does.
हाँ मैं co-location के बारे में आप थोड़ा सा अगर बता सकें.
Okay. Collocation. Let me take a new slide. No problem. Okay. I will do this later on. Collocation method. Just see that I assume a solution in the form of my basis function I1 to n alpha, any problem. Some basis function are there, phi I. My basis function could be RBF or some B spline or some other function. Anyway.
Okay.
And I put in the differential equation Ly equal to Fx.
Fx.
Right? There will be error in Ly minus Fx with the help of this y. So my Fx is there, and there will be error in the what you call solution, which I assume in terms of my basis function.
Yes.
My problem is to find alpha I. Since I have n alpha I have to find n equation.
Yes.
So one thing is that simplest is collocation. What it does is that it selects in the domain n point some way. There are different strategy. Some way n point in the domain, and you put error at this point, which I say this could be single or vector depending on xi, it is 0. So I select n point which are called collocation point and put the error 0. The moment I put error 0, my n equation are formed, and this n equation can be solved, and this method is called collocation method. Same way, somebody say I'm making least square error. That is, I take error square, so Ly whole square, and I make this error 0. That is, I will put day alpha I 0 for I equal to 1 to n. Then it is called what you call your least square method.
Okay.
So
depending on how we are formulating our error.
Yeah, how we are minimizing our
error.
Yeah. So in the collocation method is the easiest. You select n points and put the error 0. So what I'm doing here, I have taken n plus 1 points in the domain, n plus 1 points in the domain. So I assume that my solution here is u1, my solution here is u2, and so on, something like that. And so I put in the equation, make them 0 at these points, where my approximation is what you call your RBF. I'm approximating at boundary as well as in the interior of the domain, nothing else.
Right, sir, right.
So collocation means you are selecting an point and putting the error 0 there. And least square and the Galerkins are a little different. If you want, I can talk about that also. But if I go further, let me come to our contribution. So our contribution is we do differential quadrature method. What is the differential quadrature method? Like integral quadrature method, you have in the integral quadrature method, which we teach, that if I have fx dx, then we will be having a solution as w1 x1 plus w2 fx2 and then wn fxn. That is the integral approximated as weight function and f sisa. And my problem is to find w1, w2, wn and f sisa x1, x2, xn such that my error is minimum. That's what we do in the integral quadrature. Now, same way, what we say is that in DQM, a differential quadrature method, what we do is that we find weights W1, W2, Wn, so that my W1, W2, Wn give you the value of the function. So this is, and the points at which I have selected fxn, this is the value of the function, some kind of interpolation, and then f prime x, which is giving you different w. This is w1 prime for what you call wn prime for your derivative. And so my first derivative can be written in terms of the same base points, and I have to find these weights. And similarly, if I have mn derivative, nth derivative, then I have my w1 n here, that is my weight function will be changing fx1 plus w, I write, please, I write m here, so there is no confusion to you, wm, and this is nth derivative f of xm. What I mean to say is my derivatives are approximated in terms of the known function and the weight function, and problem before me is to find the weight function. Now let me explain what we have done so far is global RBF method. What we have done is global RBF method. When I say global RBF method, meaning is that so far we are considering the points, total all points inside the, or global points inside the domain, and we form the system. And invariably this system create problem before large value of n. And so another way is to consider local. So this method is global in the sense I'm considering all the points, because my approximation, please see, when I write my approximation, it is going from 0 to n. So this is for global 0 to n, global point. I want local approximation. So when I say local approximation, meaning is that though I have same point which you have, but I group a smaller thing, and my RBF is applied only for these smaller group only. I do not consider total point. So there will be approximation for these 2 points. There will be approximation for 3 points, these 3 points, and these 3 points. So I will be having, first I have the top-least matrix or top-least plus unsymmetric boundaries, or I will be having now T1, T2, T, I write M, where my domains are divided into M some part, or I say subdomains, M parts, and so this become local. Now what happened is that size of T1, size of T2, size of T3, Tm will be much smaller, and hence they do not create the problem of ill condition. But you lose certain accuracy, but ill condition is not there. That is called local RBF method. Local RBF method. And this is one of the way you can remove the ill-conditioned behavior of the solution with the help of taking large points, but you don't take all the points, you take local points and then uh, form the system. So I will form the system first for this, which is T1, then for this, which is T2, and so on. So you will be getting block top lead matras kind of matrices and solve them. You can get the solution. So that's what we do in case of what you call you have your local points. Now I come to thing. The problem for me is that suppose I am given a differential equation, and then I want to form my differential quadrature method. So my differential quadrature method means I should be able to find W prime or W1, W2, WP to the derivative which I want to do. We apply, because if I take global thing, it creates problem. So we apply local differential quadrature, local RBF differential quadrature method. When I say local RBF, meaning is that suppose I want to solve a problem in my this domain where I selected point xn minus 1 xn, then I take a group of 3 points together, that is xi plus 1 and xi minus 1, and I will try to solve in the interior. My boundary will be taken care of, because in case of DQM we write the solution with the help of the known the unknown value u. That is, I will write my first my fx. If my ux is there, I write ux, so that my ux is there, then I will write this as summation over n equal to 1 to let's say I write I equal to n minus 1, and I have alpha I phi xi, and my alpha I is to be obtained. I'm going from 1 to n, though boundary point will be coming, because my phi I is nothing but I write ui or uxi. The points having unknown point which are to be obtained. I will get matrix, u will be the solution directly. So I want to write in terms of the node point, the value at the node point of the node function, and alpha I. My problem is to find alpha I, and same way u prime x, and so on and so on. So how to find if my points are three points? If I take my 3 points, in that case you can see that if I write the things here and I take 3 points xi, or I write if you don't confuse 1 2 3 1 2 3, then my system, which if I want to find for the interpolation, my system will be u1 u2 u3, and this will be because I want to find weight function, and so I will be having right side for the to find weight function. Please understand what I am saying now before I write this, because you should understand that ux is equal to wi equal to 1 to n ui, or I write in terms of, now what happened is that I put my ux as my basis function RBF. Then the weight will be can easily be obtained, And once this weight is obtained, this can be for any unknown function also or known function also. So I take phi 1x, phi 2x, and phi 2x and phi 3x. In terms of phi 1x, I will write in terms of I 1 to 3 points. I have taken 1 to 3 points. Wi, then phi ix. Similarly, phi 2x will be I 1 to 3 Wi phi ix. And same way, I have my what you call third equation I1 for phi 3x, I1 to 3 Wi phi ix. So my unknowns will be W1, W2, and W3. Here I will have phi 1 xi. Here I will be having phi 2 xi, and I will be having here phi 3 xi. This will be phi 1 x1, phi 1 x2, and phi 1 uh, uh, x3. So this is phi 1 xi, and this is what you call phi 2 xi, and this is phi 3 xi. So you have phi 1 x1, phi 1 x2, phi 1 x3 first row. So you have my first equation. Then you have phi 2 x1, phi 2 x2, and phi 2 x3. Then you have phi 3 x1, phi 3 x2, and phi 3 x3. I have this equation. If I take phi 1, phi 2, weight function is used. Always please try to understand in DQM, when you want to find weight function, you use a basis function and put basis function equal to the, in terms of the same basis function, your W1, W2, W3 can be obtained, in this case 3 point, or W1, W2, Wn can be obtained in case of n points. And ultimately when I get W1, W2, W3, then any function can be approximated with the help of W1, W2, W3 for 3 points. So this is for interpolation of the function. Now same way, so this function when I write, please understand me, when I write for my quadratic function, multi-quadratic function, you will understand very easily, because my phi 1, because my quadratic function phi r is under root r square plus c square. So when phi 1 x1, this will be only r will be 0 because distance is 0, and it will be only under root c square, so you get c. Then my second function will be under root h square, because distance between 2 point and 1 point is minus h or plus h, whatever you call, h square plus c square. And same way this will be 4h square plus c square, because distance is 2h from 1 point of the C3. Now again I come to the second, so phi 2 x1 is again this same thing. So I have h square plus c square. This will be again c, and this will be again h square plus c square, because this is second point. So this distance and this distance is the same. And same way this will be 4h square plus c square. Am I right? 3x1, yeah, 4h square plus c square plus h square plus c square plus c. And you have your W1, W2, W3 is equal to the value of the function there. And I write phi 1 x1, phi 1, phi 1 x2, and phi 1 x3 for the first function. Right. So you have this. Then this equation can be solved and solution can be obtained. And I can write solution if you want. I have the solution with me. Otherwise, this is symmetric matrix and solution Canvas rule anyway, it is solvable. I know the solution. If you want, I can write the solution. Otherwise, one can find the solution because I want to do by less time. So I want to do something more. Now, the way I have found first thing, same way I will find my derivative. That is phi 1 prime x will be written in terms or r will be written in terms of I1 to 3 phi 1, sorry, w1 I write 1 because this is for wi for prime, and you have what you call phi 1 xi. This is what one equation will be. Then similarly I will be having for phi 2 prime I, which will be I1 to 3 what you call wi1, you have phi 2 xi. I write I write x here, so no problem. Okay, and then you have phi 3x is equal to I1 to 3 wi1 phi 3xi. So you have this thing, phi 1 prime, phi 2 prime can be obtained, the equation can be formed, and again you will get the symmetric equation, and for derivative also you can find derivative. I already found. Put the in the matrix, you will find 3 by 3 matrix. What I mean to say is w1, w2, w3 for the 3 by 3 matrix can be obtained. Double derivative same way can be obtained. Once you get the weight function, use in the problem. So please now understand what I'm saying, because this is my last part, which you will understand, then you can solve other problem too. So I'm given this problem, and what you call my thing is that this is between 0 and 1, and I have u0 is equal to alpha, u1 equal to beta. My intention is to use local method so that I can easily solve the system. So this is my x0, this is my x1, this is my xn minus 1, this is my xn. Now when I do so, I need to find weight function. I have already found. So I will solve, because my u0 and u0 is known to me at 0, u at 0 is alpha, and u at 1 is beta. So I already know them. What I do is that I take x1, and I know for x1 my local formulation. So I will be having a matrix based on x0, x1, x2, x2, and I will have my matrix T1 from the what you call my double derivative of the weight function I put there, and I will be having here u0, u1, u2, and this is the matrix T1 of the double derivative. I hope everybody try to understand me what I am saying. This is a local property. So I will be having f of x0, f of x1, and f of x2. I have this equation for these 3 points. Now when I go to next point, then I will be having same kind of structure T2, and this will be for u1, u2, u3. u1, u2, u3. Because I'm taking 3 point local point, so I will be having T1, T2. What I mean to say is I take 1 point before it, 1 after it, so 3 point local point for each point. I will be having total Tn minus 1 matrix here, and u1, sorry. This is un minus 2, un minus 1, and you have un, and then you have accordingly f of xn minus 1, f of, no, sorry, 2x of n minus 1, f of xn. Uh, this is a system which I apply my differential quadrature locally for x1 point, then x2 point, then xn minus point. I will be having this kind of structure. This is to be assembled. So I'm sorry, this is not 2. This is, yeah, this is okay. I'm sorry. So you have u1, u2, u3. Now you assembled, so this system, and when assembled, you get your system, which will be of course, T1 is full matrix, T2 is a full matrix. When you combine U1 to be added, the row of U1 is to be added with the O1 U1 here, and row of U3 is to be added, U2 is added with here, and so on. The first row, which is known to me because U0 is known to me, so I remove the first row, and the boundary condition is taken to right hand side in the from the second row, and I can form my system. So what you have is that ultimately I assemble them, which is nothing but something like uh, assembly of T1, T2, T1 and T2, because T1 contains U0, U1, U2, and T2 contains U1, U2, U3. So U1 component and U2 component in the second equation will be combined with the T2, and uh, similarly the third row here and second row you will be combined with the T1, and keep on doing so. So you assemble, which is much easy, and then you have total matrix system here, where this is the assembly of uh, Tn minus 2 and plus Tn minus 1. And you have the system which will be of order n minus 1, yeah, interior point n minus 1, precisely, because the first row will going there, last row going from there, and others will be combined, and you will be having something like this: u1, u2, un minus 1 is equal to the right hand side, which are assembled. The first will be assembled, rest will be same. No, they will be assembled also, and you have a right hand side. Solve it, you get a solution. And I must tell you that we have solved this problem. I just tell you what is. I have 5-6 minutes. Please, can I take that, Professor Lakvir?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
So I tell
Yes, sir.
you,
Sure.
what is the problem now. If I don't take differential quadrature, what happen? Suppose I have a problem of the type du by dt. Please understand my point, because if you get the concept once, then it is very manual work. If I use my solution here in terms of basis function, then I write ux2 in terms of alpha it phi phi x or phi r, whatever way. If I x bar, I write x bar here, right? Now what happened is that uh, phi will take care of du dt by dx2, right? So I will find double derivative of phi x if I don't use dqm, then, and I will have for left side the alpha 1 prime plus phi 1 x bar plus alpha 2 prime phi 2 uh, x, and so on, alpha n prime phi n x, and accordingly there will be right hand side in terms of double prime, in terms of double prime. The problem is that this comes as a full matrix, a full matrix, and you have alpha 1 prime, alpha 2 prime, and alpha n prime, and is equal to something in the right hand side. Now this is a problem, because this A is invariably, if I take global thing and this way without DQM, this way. So what happened is that there's a full matrix. You take its inverse, it will create its own problem. It does create its own problem, right? Now, if I take instead of DQM, what DQM does? DQM does that it writes the equation. If I take DQM, simple 3-point local or otherwise, then I will write this as alpha I weight in terms of x and in terms of weight function. So what happen is that my first equation, if I write, then I will be writing day u1 upon day t, and the approximation of day 2x2 in terms of interior point I or 0 to n boundary condition will be taken care of by 0 and n, and you have this alpha is there. So I write weight wi, then u prime, or the differential quadrature for u prime. So I have in terms of again a basis function phi I x, which is wi2. So for this is for u1. So my thing will be first weight function. So I1. Then I have day u2, day 2t, alpha times wi2, 2, then phi I x, and so on. So there are weight function for each u1, u2, un. What I mean to say is you will be having un minus 1 day t2 corresponding equation here. And here you will get a system of the form u prime is equal to a matrix plus unknown thing plus some boundary condition f. This kind of system. Now try to understand me. First thing is, you note that I have a system. I'm talking about DQM. I have system of this type. Y prime equal to Fy. My system depends on unknown y only. There is no other terms in time or other things. And Runge-Kutta method or can be simply applied, or some method which is better than Runge-Kutta can be applied, solution can be obtained. Here, before applying Runge-Kutta method, I have to bother about the matrix A, whose inverse I have to take, and this creates its own problem. And then I have to find the solution. So basically, this formulation we find easier. And I just tell you that what we do in our work is that for nonlinear equation, we form the system of ODE and solve by the Runge-Kutta method, or a method which is better than Runge-Kutta method, invariant of it, such a way that nonlinearity does not create a problem, because when I solve ODE, the Fy, whether linear or non-linear, Runge-Kutta method does not consider that. And we are getting good solution. We have done in 1 dimension, we have done in 2 dimension, and we have done in the 3 dimension too. Anybody interested in our work in this type, there is a PhD thesis which is completed. Sanjay Kumar, Ram Jiwari, and R.C. Mittal. You will find 4 and 5 papers. In one paper, we have given the whole methodology in the beginning paper, whole methodology and how to find what you call your local 3-point solution. Not only 3-point, 5-point, 7-point we have given in that paper. All local formulation, how to find the weight function. In fact, explicit form of the weight function is given. So what I mean to say is, we found the local method much better than global accuracy wise, and we have solved problem in 1, 2, and 3 dimension as well. So this much from our side. Thank you very much for the listening, and I will consider some question if you have any. Please pardon me if I've taken more time because of the thing which I wanted to explain something, and in between I might have taken more time because of some of the concept I have to remember well. Yeah, that's all. Thank you.
Thank you very much, sir. It's really very thankful us. So any queries from the participant side?
No, ma'am.
So we are
Hello.
So we are really very thankful to you, sir, because you always say yes for our any type of the workshop or seminar or the conference is there. You are one of the biggest strengths for our department. We are really thankful to you, sir.
Sir,
Thank you.
sir, I
Thank you,
agree
Dr.
with Lakhveer, ma'am.
Thank you, madam. Thank you for your nice words. Let me tell you, I have decided 3 years, 4 years back. Before that, of course, who is calling me and why he is calling me, all these things comes in my mind. But uh, I must tell you, by nature, saying no is very difficult for me. So I do consider these points earlier. Now I have, if somebody approach me and if possible, I will go. I will go, and I must tell you that I never ask for money. How much you pay, whether they pay or not. I just go and give my talk and come back. They give something me, I take it. I never say no. And why should I say no? I'm telling you very frankly. But I never, before it also, I must, when I IIT Roorkee, I never bother about money part, but I bother in this much कि मेरे को पहले क्या दिया था तो मैं डिसाइड कर लेता हूँ कि मुझे टॉक कैसा देना है या देना है कि नहीं देना, पर अब मैं उसकी भी चिंता नहीं करता हूँ. So this is what it is. By nature, it's very difficult for me to say no. And whatever I know now, I have done everything. Whatever I could gain, I have already gained. So really, I'm always helpful to the persons because God has given me enough. No problem for me. That's all.
Thank you, sir.
Thank you, sir. Sir, it's really very great for all of us that your
Thank you.
expert knowledge and the profound expertise uh, is really going to help us in our academics as well as in our research. And I hope
You said to me RBF, that's why I took. Otherwise I would have done something different. Yeah, because RBF is latest work. This is my last 4 years work. RBF.
okay. Thank you very much, sir. Thank you very much, sir, for providing all the detailed content and having interactive session with all the participants. And I am thankful to all the participants also for they really make it worth in the true sense. So
Thank
thank
you.
you to
Thank you very much, madam.
thank you, head of the department, Professor Alka Tripathi ma'am, for her continuous support. And thank to all the faculty members of the Department of Mathematics. And tomorrow we will again connect with the same link, but at 2 p.m. because tomorrow we will have the tutorial class. So let's meet tomorrow at 2 p.m. with the same link. Thanks to all of you.
Thank you, madam. I will just leave it.
Thank you, sir. Thank you,
Thank you,
everyone.
sir. Thank you, sir.